For pixels, the atoms of digital space. So I'm Alan Cation. I'm a computational designer. I'm also an artist and an educator, and happen to be the lead computational design engineer at 510. I also teach classes at Pratt Institute. I've taught at City College, and I'm a member of Design Morphine, which is a design collective that operates online as an education platform as well. So at 510, we provide innovative design engineering solutions for unique light and video installations in the built environment. We have a background and connection to live entertainment. So we also aim to help designers and visionaries navigate the landscape of LED technologies to inform the creative process and enable the development of project-driven bespoke concept solutions. So rather than existing products limiting the innovation and creative freedom of designers, projects can inform the development of new product solutions. We take a holistic and wholehearted approach to innovation, and by continuously investing in research, development, and experimentation, we offer unique tools to realize our clients' artistic expression. We take design concepts from our clients. We use our expertise in various engineering disciplines to design and build bespoke display installations. We basically take projects from the ideation phase and build them with our unique creative engineering approach. So my background is in architecture. Probably half of this presentation will be about architecture. I've been a computational specialist for pretty much the entirety of my career, which has given me it's allowed me to have a hand in a lot of different types of projects. I've worked on hospitals, skyscrapers, museums, airports, all over the world. And if we think of a brick as the atom to a building, well, we are thinking of a pixel as the atom to a digital display space. At the end of the day, we want to free the pixel from the standard approach. So we're looking to be bespoke with our solutions, and we continuously aim to make pixel arrangements free, organic, and pleasing to the human eye. All right, let's go on a little side quest. So I talk a lot about computational design. Have any of you ever come across this? Is this something? Yeah, maybe a couple, but maybe not everybody. So what is computational design? If you're kind of wondering what the hell is this guy talking about? Why is he here? Computational design is a methodology. So we use computation, not just computers, but the logic and coding process of computation to generate, analyze, and realize form, space, and systems. So it's about defining a logic and a process in the design process. So rather than just drawing and coming up with outcomes in an analog way. So I'll go through a brief history. So a lot of this we can trace back, and maybe arguably goes further back, but Antoni Gaudi, I'm going to put as a pivotal key player. He was a proto-computationalist. And what he was doing was he was actually designing with the laws of physics. So he had this catenary chain model. So if you've ever been to Barcelona and the Sagrada Familia, I mean, I think it's probably one of the most amazing buildings on planet Earth. But the entire structure of that was designed by putting weights on strings and hanging it. So the entire structure works purely in tension when you hang it upside down. Well, the cool thing that Gaudi discovered is that if you hang something purely in tension and then you flip it upside down, that becomes purely in compression. So he's able to like literally design this stuff by hanging chains and then flipping it upside down. He's probably a century or more ahead of his time, thinking of ideas of form, surface, and space in a way that few other people were thinking about. He's also my favorite architect. There's a quiz at the end, so you better remember that. Buckminster Fuller, another kind of key player in like the early phases of computational thinking. I mean, he really advanced the idea of systems thinking and thinking about, the world in a holistic way. He was definitely more than just an architect. He was also a philosopher. He talked about society and like thinking of the systems and relationships that really make up the world and what we live in. So this house on the left is his first dome house. I actually lived a block away from that in Carbondale, Illinois, where I went to school in Southern Illinois University. So that was fun to see every day. Frei Otto, he was another figure taking the lineage of Antoni Gaudi. He also used analog form finding experiments. So he was taking soap film, generating minimal surfaces. He was also taking, tensile fabric and creating little models from that then actually became the literal structure that they used in the buildings that he would create. So again, also designing with the laws of physics in a very systematic way, even though it was analog, that has relationship to what we do now in a computation space. About the time that Frei Otto and Bucky were going on, the 1960s and 1980s, these guys were experimenting in actual computing with computers. Ivan Sutherland was basically invented modern CAD. So his program Sketchpad here on the bottom left, that was in the 1960s. In the 1970s, Nicholas Negroponte was dealing with the idea of, how do we live in a digital environment? So they had this CNC machine that was constantly reconfiguring space for these gerbils to navigate in. And then they were documenting how that kind of affected the life of the gerbil. And an evolutionary architecture was by John Fraser, and he was really thinking of ideas in the 1980s about how do we take evolution and ideas from evolution and put that into the design process. So all of these kind of were based off of early ideas of cybernetics, computation, and artificial intelligence. Zaha Hadid is probably, the contemporary example, I would say the poster child in what now is pretty much like synonymous to what computational design is. Zaha is basically the benchmark that, everything these days gets compared to. So a really cool, awesome figure, rest in peace. She died about 9 years ago. All right, side quest completed. We are done. Congratulations, everyone. And I just want to reiterate, when we're talking about computational design, we're talking about designing with scripts and designing with code. We're not just talking about 3D modeling in a computer. That is a mimicry of an analog process. So it really has to be logic-based and it has to be system-based. So we use a program called Grasshopper for Rhino. That's a visual scripting interface. We also use C# and Python text-based coding. So all of these different kind of tools at our disposal are what we deploy in a computational design process. Applications of this, we use it for generating geometry, automating form production, parametric modeling. So if I say parametric, that's maybe synonymous with computational design. And also, populating a form with various parts and pieces. We also, through the pipeline, analyze this geometry. In architecture, we are often doing performance-based analysis. So we're looking at daylight, we're looking at radiation from the sun and all of these other environmental factors. And then we can optimize that and optimize kind of building shades and solar shades to help mitigate sun coming in or help bring more sun in if that's the goal. So it's also used by structural engineers to optimize for structural form. And then all of this too, we can use the computational model to help optimize for buildability and just directly go from the part in the model to fabrication. So a lot of this is we're automating, the pieces of our building that go directly into fabrication files that get 3D printed or CNC machined. So all of this, we use as a pipeline, or it's like multi-phases throughout the process of design. But why do we really do this or care about this? I mean, I think as humans, part of our condition is we want things to be beautiful. We're attracted to the natural world. We like things that are organic. Yes, I'm going to speak for everybody. Okay. If you don't like those things, shh, be quiet. But yes, at the end of the day, we've always kind of strived to look at nature and be inspired by it. We also have to deal with real world constraints. So there's, in the modern world, we have costs that we have to deal with. We have site that we have to deal with. So there's all these kinds of budgetary constraints, and a lot of times deadlines are fast, rapid, that we have to move quickly to get projects done. Well, computation helps enable that process in a better way. And at the end of the day, humans, we're always wanting to do amazing things. We're reaching for the stars and we're constantly looking to improve, hopefully with the idea to advance the human experience. I mean, arguably technology doesn't always do that, but I think as an ethos, that's kind of what we're aiming to do. So I've spent my background as a specialist in design technology departments in architecture firms. I worked for INEAD Architects and Cohn Peterson Fox, or KPF shorthand. So this is the kind of work doing formal panelization studies, design for architectural projects, and then analyzing those projects. This is an early project, Dragon Shell Pavilion. I actually did this in grad school. This was kind of a pipeline from design to fabrication. So this project was using the same techniques that Gaudi and Frei Otto were using, except I digitally simulated that. So we can use physics solvers in the computer to then mimic what was happening with the hanging chain model. So this was designed with gravitational forces to create a shell that works purely in compression. And then we can use computation to then add pattern articulations. These had openings so that it could allow someone to see through, and also had shading so it would block out sun. And the whole thing was designed in a computational model that, was the process to laying it out for fabrication was also automated. So we could lay out sheets and then take it straight to the laser cutter and build it. Swarmscapers, this was another research project that I did in graduate school. This was an autonomous mobile 3D printing robot. So the idea of this was also, we were thinking of ideas of artificial intelligence and how multiple 3D printing robots could work together basically to build architecture autonomously. This was our little prototype, but really the idea here was how can we think of architecture as this autonomous machine. So if a bunch of little robots working like ants together could then build and excavate buildings, then what does that look like and what does that mean for the world? This is also on Unstructables, so if you're curious about making this project yourself, do so at your own peril, but you can visit this at Unstructables and check it out if you want to learn more. So I've worked on a lot of facades. A lot of facades are pretty much one of like a prime example of a use case for computational design. There's a logic to it. They're systematic. There's a lot of moving components that need to happen rapidly. So computation is like really just perfect for designing these things. So when we do that, like what do we do at the end of the day? We start with a form. We have facade elements, so we have maybe a set number of panels that we're dealing with. And we use computation to take those panels and divide the form up and distribute it on the form. So when you have the form and you use a computational model to align and distribute the panels, then you get the output of the building that's to the right. So this is an INEAD building. This is in New York City on the Upper East Side. If you have time to check that out, it's a pretty cool facade. And we call this process panelization, by the way. If I've said that, if I'm talking about panelization, really I'm talking about distributing architectural panels on a building facade. So this is the same process. We have panels and then we distribute that and then it aids in, the outcome of the built project. So as a computational designer, I build a lot of tools. This is, I don't know if you're familiar with Grasshopper at all, but Grasshopper is my primary tool for doing my job. So Ankylosaurus is a plugin for Grasshopper in the Rhino geometry engine. So all Rhino Grasshopper plugins have, for the most part, animal names. That's just the theme. Everybody who makes plugins we'll name it some animal, and I always thought dinosaurs were underrepresented in the plugin ecosystem, so that's why I named it Ankylosaurus. And I really like dinosaurs. So yeah, if you want to download this, this is online, it's free, open source. It helps with subdivision of surfaces. Also use at your own peril. So yeah, this is a facade population and distribution tool. I built this really as an aid for other designers. So I use it myself, but it also was used by many designers at the firms that I worked in. So it has a custom user interface and it's meant to quickly allow designers to populate facades and undergo design studies. So we have to do this a lot. Most of the time, we have ideas that we think a building should look a certain way. So we need to kind of rapidly iterate and kind of discover options and possibilities. I mean, I think I've encountered at 510, that's also true in the engineering space. So yeah, this really just helps us quickly iterate and design the things that we're doing. This is another project that I worked on at INEAD called Yangtze River Estuary. It's a Chinese sturgeon nature preservation center. We designed this in 2018 for a competition. We actually won the competition, but because the runner of the competition lied about the budget, we went way over budget, and then the mayor of Shanghai killed the project, unfortunately. So I think it went from, that building to more like the small building on the right. Um, anyway, so it's a big pool meant to preserve the Chinese sturgeon. This is a lab facility on the inside. This is an interior shot of one of the lab pools that helps grow the sturgeon at a certain phase in their life cycle. But the roof that you see here above, everything above the black line, that was 100% computational. So all of this was done using a script and designed with a script. So this is the logic of that script. We have it was really built, the only kind of analog part to this were 8 input curves. So, we do still have to define based on a lot of different things, uh, the specificity of what the form is. So really we can take the curve and move those curves around and all of the other geometry updates automatically. So the skinning of the tensile membrane, all of the structure, all of the interior baffles, and all of the other sub-architectural elements were all generated out of this script, and all based on the 8 input curves from Rhino. And here's some more interior shots. What was great about having this as a script too, we were constantly working with uh, model maker and going back and forth. So we could just tune the script so that it could be easily 3D printed in the way that we needed to, in the resolution and the scale, and also make little prototypes and mock-ups. So like in architecture, computation in the LED design space, it's about managing complexity. So really we're trying to free ourselves and free the LED from the standard approach. Um, we really are dealing with the physical arrangements of pixels. We're trying to make them more organic and make pixel displays, more pleasing to the human eye and make really cool applications for this stuff. So one thing that computation helps us do, it also helps us expose all of the data and information that is needed to design a pixel display. Oh, aha. Technical difficulties and my video was not playing. Here we go. So this project is called Awakening at the Wynn. This was a 510 project that really dealt with a complex stage design. And I think due to the complexity of this project, we really needed computation to design and execute the whole stage. Like we had a lot of different panel types that we were dealing with, a lot of different variation, and a lot of moving parts to this display. So computation was really kind of a necessary facet in helping get this thing delivered. All right, back on track, I think. It's not playing. There we go. Okay, so like I said, we made computational model for the panelization that outputs the panel design, and it associates it with all of the various structural elements. And all the pieces are associated together as one thing changes, so does all the rest. And I want to shout out Ben Price. I don't know if you, there he is. Ben did the computational modeling for this project and really made this thing happen. So, like all computational models, we start with breaking it down into its logic and the component parts. So we've got to identify the circles of the stage. That's the main input. And then once we have that, we start to subdivide this thing. We break it. This thing was broken into like a substage, and then each substage then broke into further structural elements that then pairs down and continues down until the LED system is panelized. Rationalization is really inherent to the design and engineering of this project. So while we are, discovering the logic and breaking this thing down, it was really designed with rationalization in mind. So this thing, all of the transparent LEDs, there's a transparent LED film. Um, they have their own rules, and they were all basically designed so that we have 10 unique pieces. So we only had to design 10 of these pieces that then rotate around to conform and make the rest of the display possible. The same was done for the center stage. These were a different type of panel. They were custom designed, typical FR4 PCB materials. So it's a fiberglass material. And we had 20 of these unique panels that then could rotate around and then complete the stage. But the cool thing with the computational model, we can evenly distribute the pixels. So no matter how the shape changes, the pixel distribution is still maintained with its own set of logic and rules, and it updates accordingly as the geometry changes. We're doing the same thing for the fiberglass modules. Those all have to have a custom framing system, and there's a rule set that goes into that framing system that we can basically automate, and then as things might need to change, it just reloads through the automation pipeline and then updates accordingly. So all of this is done in the computational model. So this was helped us throughout the entire phase of the design and delivery process of this project. So the concept, is ideated in the computational model. The rationalization and analysis is baked into that. So is the pixel distribution. We can also use this to automate our documentation. And then we can also output all of this for manufacture. And this also helps in the raster mapping. So we're able to automatically take that from our pixel distribution and get raster output to give to the content creators to help create content for the display. All right, so the last example was an example of a 2D display, which has its own set of complexity. We also frequently work in volumetrics and engineer custom volumetric displays, which kind of has its own set of complexity to it. So whatever complexity happens in 2D, that's kind of taken, and it's a little bit different, but we can kind of add to it when we're thinking of a digital space, especially when we get to things like raster mapping and just the general output of the models that we're working with. So all of these displays, you have Susan Narjuli is the designer for the one on the left and the one at the top. This is in UC Berkeley, and the one at the top is Oklahoma City. And then the one at the bottom right is T-Mobile Store, our Flatiron project. So all of these were basically a bespoke product that we did for each of these projects. So as we enter this space, we have to deal with the complexity. And that's why, in order to help manage the complexity of realizing new volumetric displays, to be specific to designer needs and their given context of wherever this display is, we developed computational tools to kind of quickly and seamlessly iterate through this process. So all of this, we have a tool that helps us basically rapidly create options that we can iterate as things change. We can change the panel size. We can change the length of the strand, how many pixels go into the strand. We can change whether that strand gets cut in a certain way based on some kind of input form. And really what this is doing is it allows us to design flexibly. It's kind of we kind of have this base product, and it is a product approach that we're keeping in mind when we're thinking of building the computational model for this. So what it really allows us to do is free us from the standard typical box solution or the off-the-shelf solution. So we really are invested in customizing this stuff. So if the pitch needs to change, panels need to change, we can do all of this associatively and relatively quickly. So all of this are exercises in mass customization. All right, so this is further iteration. As this thing updates, we know how many strands, where they're cut, and all of this stuff. It really becomes necessary to keep track of the data and the information. We need to know the pixel count. We also need to know power and heat information. So all of this stuff is tracked within the tool. What it also allows us to do is it allows us to create a connection to ECAD software and deal with the mass customization of electronics design. So we're really like using this as a handoff engine. It goes to mechanical engineering, it goes to electrical engineering, and kind of allows the various sub-disciplines within 510 to work together. All right, so this was another cool and fun project. This is the last thing that I'm going to show. I'm actually running quicker than I expected on this. All right. So this is a Mobius strip. It's a double-sided display. This is a fun project. I think everybody wants to do Mobius strips because why not? They're cool. They spin on itself. It's a fun and interesting challenge. So what is the actual problem here? So it's easy to mathematically define a Mobius strip. We could take this, there's an equation, we basically use an equation to array the points, and we can get a surface that builds this Mobius strip. But then when we begin to subdivide that and panelize it into triangles, well, the issue with the pure mathematical approach is that every single one of these triangles is unique shaped. And due to economy of scales reasons, we want to use as few pieces, few triangles as possible to break this form down. So, I mean, there's other ways that we could break it down, but we have this triangle panel that we are working with, and that's how we want to distribute it. So we're just using one panel. So the problem becomes, how do we take a form like a Mobius strip and populate it only using one triangular, equilateral triangle panel design? As you can see on the bottom one, well, maybe you can't see it, they're all messed up. Like all of these panels are actually overlapping. None of that physically works in reality. So what we can do is we can actually simulate the physics of this. This is using the same exact concepts of what I was talking about with Antoni Gaudi and with Frei Otto, who are doing their early experiments in analog designing with the rules of physics. Well, we can computationally simulate the laws of physics using Grasshopper and Kangaroo. So this model, what this is doing is it's using bending forces, and it's using like the size constraints of what our panels are to basically force this Mobius strip into a strip that is physically buildable and that is actually mimicking the processes if you were to take a single strip of paper and fold it in on itself. So that's basically what this digital model is doing. So the cool part is we can then approximate and take this thing as a double-sided Mobius strip and make the thing work so that it all is populated with one single triangle. And this is the output of the Mobius strip, double-sided. little video run around. Okay, so I'm wrapping this up a little bit. Really what we're thinking about and what we're talking about here is one model to rule them all, and that is the computational model. That's for all you nerds out here. Um, so the computational design model, it's really the methodology in which we're talking about. So I guess one thing that we want to take away from this, really just kind of asking as an industry to at least adopt some of these methodologies, so that it helps enable us all work together. But at the end of the day, I think what we're trying to do is make as cool of stuff as possible. So we're trying to like push forward. This is why we use these processes at 510. And it's just, I think, industry wide, so we can put extremely cool things into the world, make things awesome, and make displays that we couldn't make 10 years ago. And that's my talk. Thank you.
Sorry, I took a little bit, so apologies if you answered this already, but, how, like, I think is your math background, how much of the day are you spending, like, really doing math?
I hate math, but I do math a lot. I would say, I'm more of an applied math person, so my math background is you give me an equation, I can put it in. I'm looking up equations constantly, so it's not like, oh yeah, I just know how to do an equation for a Mobius strip. That's not like off the top of my head knowledge. I mean, maybe like basic stuff like circle math is pretty easy, but it's, uh, yeah, I'm not a mathematician. Like my background is, architecture and design. But I do find myself using math a lot. I would say it's important to know it, but it's also, I'd say if you are better at math, it probably helps doing this kind of stuff. But it's not like a necessary facet either. It's like if as long as you know how like the rules of math work, you can kind of use it to help in the process. Yeah, I don't know if I'm directing this.
I'll do it.
Yeah.
Go ahead in the front. Just give 1 second in the front.
Yeah, this is a self-interested question.
All right.
As somebody who lives on the other side of what you do and is doing computational generative content for these kinds of services, using Touch Designer, Notch, etc.
Right.
When you are designing one of these systems, is um, making sure that the UV maps will generate octets and a parameter that you adhere to.
So don't forget, I know it's, can you summarize the question for the live stream?
Ah, yes, live stream. So you're asking if the raster mapping is inherent to our process, or
Can you use the octet as the minimal, as the atom of the raster map? Because as you probably know, like when you're doing computational generative content,
yeah,
graphics cards just like octets, they work much more efficient when the raster is divisible by 8.
yeah. We do. So whatever the display is, because sometimes we're using different kinds of LEDs and different types of pixels. That whatever like whatever it needs to be for the raster is what we bake in essentially. So it's like, okay, if it needs to be 8, sometimes it needs to be fewer, sometimes it needs to be more. Uh, when that happens, that's just kind of, we set that as a parameter essentially. So that is really just like a multiplier that we use to kind of then generate in our like raster mapping tooling. So if that answers your question.
Yeah, I just think when I could rasters with like numbers in there.
Yeah. No,
Other dimensions.
Yeah. No, we try our best not to do that. Cool.
All right, one in the back?
Yeah, so I'm generally familiar with the concept of like procedural and generative design. These computational design, curious to see these being synonymous, or is there a distinction you can see between what we call computational design and more general principle of procedural generative design?
Yes. So the question is, uh, the terminology computational design, is that synonymous with generative design or procedural design? My short answer to that is yes. Really, I,
Sorry, no, but let's get some more background to the question. When you talk especially about things like organic forms,
yeah,
organic forms are not a product of computation, they're a product of processes. So if you're trying to simulate those things, I can understand how computation design is a vehicle for pre-describing processes.
yes.
Here, to just have more color to the question.
Yes, so if computational design is like a vehicle for processes and organic forms are the result of processes, not computation. Well, yes, so I think like computational design to me is sort of its own, uh, I would say it's its own discipline that is an umbrella. And I would say that procedural modeling and generative design of what you're asking is within that umbrella. So it's really just like the computational design space is like designing with logic, designing with process, thinking about process. So if you're procedural modeling, that is to me a subset of like computational design. So I would say yes, like that's why my short answer is yes, it is synonymous, but it's like it's kind of a subset and a subcategory of computational design as a catch-all umbrella discipline.
Just gonna take one of the live stream questions first. Can you read it? Right there.
The question is, isn't a Mobius strip by definition a single-sided display? Okay. All right. You caught me. Yes, that's the whole point. It's continuous, same surface.
Okay.
Yeah.
What are your thoughts on applying computational design for real-time dynamic structures that would have to apply that process as part of the actual fabrication in the end? Dynamic result is continuously adjusting
Yeah.
the physicality of the object.
So the question is, what do I think about the computational design process if that was to real time influence what was happening in the fabrication process? I think I summarized that. Actually, I'm gonna go back a sec to, oh no, it's playing sound. Sorry, computers. So this is a roundabout way to respond to this question. Please. So this was one of my early research projects. This was tackling this idea directly, at least like the ideas around this project. So not everything is, I'm not showing all of that, but like one of the ideas of this is that like, what if these robots are actually, taking in like the information and adjusting in real time based on environmental data, based on weather factors, based on all of these other kind of site conditions that allow us to, you know, build and design in real time in space. So I think it's a cool idea. I've done research into it. It's something that I've explored with students in the past, teaching architecture classes and like teaching computation within architecture courses at City College, a little bit at Pratt. So I mean, I think super interesting space to explore. There's a lot of people that have done research into thinking about what you're asking. So I don't know off the top of my head if right now there probably are examples these days of people that are kind of pulling this kind of thing off, but I think, we're maybe still pushing in that direction and not quite exactly, I don't think we're there yet, especially at a large scale, industry-wide type of process yet. But I think it's an awesome idea, and I've dabbled with it for years and thought about it for years.
Good, one more, yeah?
When you're designing, how much is your approach like looking to figure out the logic? So if you have a concept, looking at the logic to try to get the result closest to what you're imagining versus having like a concept that's a problem and trying to figure out when applying logic, what the solution is.
So the question is, how much of the approach is trying to use the logic to get as close to what I'm presented with at the start, versus using the logic to kind of come up with a solution that might be a little different? Does that summarize that correctly? Maybe I'll go back up a few more slides to, or no, sorry. Gotta go down a few. Where is that slide? I'm sorry. It's up. So just to respond to that, I would say it's 50-50. So sometimes we're given a problem, like, especially in like engineering, we're trying to get as close as possible to what a designer would give us. So I think in a lot of ways, we take what is given, we have to break it down into its logic. So a lot of like what I would do in my job is like try to just understand the subparts that would make it up and then get a solution that, might look a little bit different, but it's as close as humanly possible to what the design intent of that is. Now, there's also, when we're talking about procedural form making and the question like that came out, sometimes we're not necessarily looking for an outcome. So it's kind of a both and answer to your question. Like sometimes it's one, sometimes it's the other, and sometimes it's like you might be surprised when you're working out a problem and like, maybe you are getting it to be as close as possible to the thing that you're presented with, but in that process and breaking it down into its logic, you're discovering new things. So maybe you have new discoveries and new outcomes and new possibilities that are kind of born from the original idea that was done in a more analog way. And then when you systematize it, you're like, oh, actually, it can also do this thing. It can also do this. So I think there's like a lot of discovery that happens in that process. That answers your question.
Thank you.
Cool.